Welcome again to another episode of Empowering Introductory Algebra, the series developed to assist students to gain an understanding of the algebra fundamentals necessary to succeed upon entering those college-level courses. Hi, I'm Bob Young, Assistant Professor of Mathematics at Brevard Community College. Along with my excellent support staff of WBCC, we will present algebra lessons that you may work on anytime convenient to you. Now, where we left off was applications involving rational equations. So let's go ahead and look at that graphic one more time. And what we discussed at the end of the last episode was ratio and proportion. And we discussed some recipes where you might want to make some more or less of a certain recipe of Italian bread. And we saw how it worked in the kitchen. And then we saw how marine biologists could use ratio to maybe estimate the number of blue whales given certain information on ones they tagged. Let's talk about the proportion side, looking at some examples now. All right, so when we go to the examples here, similar triangles, corresponding angles are congruent in them, and corresponding sides are in direct proportion. So we're going to go ahead, I made a large triangle here. This is big triangle, ABC. And we're going to say that it is similar to little triangle here, itsy bitsy triangle DEF. All right, so when that's true, what we're going to try to do here is find side B in red using some proportionality and some ratio here. See, so looking at these, and you see sometimes in real life, see, they might have a giant space shuttle there and a small scale model of it and so forth. I mean, to the exact details and specifications, here's how they do it. So if we're after side B in triangle ABC, we're going to look at this one and say, which sides would match up? And you would have to say that EF matches up with what side over here, BC, and DF matches up with AC. So if we want to make a proportion out of this to get side B, it would be 4 to 6 in this triangle matches up with what to what in the large triangle. I think y'all see it out there, 9 to B. So now we can compare them here. We've got a nice, rational equation. So now to solve for B, we'll go ahead, since there's only two of them, and take the cross products. 9 times 6 is 54 equals 4 times B is 4B. And to solve for B now and get this side we're after, we divide both sides by 4, and we end up with B. Let me bring that over here so I can write it better. Put it right under B over here, is 54 over 4. Now notice we have a fraction that reduces here. What number goes into these two, the top and bottom? 2 will reduce it. So 2 goes into 54 27 times, 2 goes into 4 twice, and we end up with 27 over 2, which we could also, if we wanted to call that, it could be 13 1/2. So side B would be that relationship. And then we could also find side C if we were after it. Now look at these two triangles. If we were after C in green here, we could say that looking at the smaller triangle, we could say 4 to 5 in the smaller one equals what to what in the larger one? Well, 4 matches up with a 9, 5 matches up with the C. See, so there's all kinds of interesting uses here. So we could cross multiply real quick here. 4 times C is 4C. 9 times 5 is 45. And then we could divide both sides by 4. So side C would be about, 11 1/4 if we were after this side. So now we have them in direct proportion. So just another use of rational equations. Now, the next one we're going to talk about is distance. Okay, so the distance formula here, rate, how fast, times time, how long, always equals distance, how far. Now, before we do this example, did y'all ever think of how the airlines use this in estimating time of arrival? Well, they know how fast the plane usually goes, and they know the distance. Let's say you're going from Melbourne to Boston. They know the distance, so they can get the time by dividing the distance by the rate. So that's how they estimate time of arrivals at your airport. Well, when they're not have any delays or anything, you know how that goes. But anyway, just an example out there. Now let's look at this one. Joe drives his truck 20 miles an hour faster than Jane drives her car. All right, this is not meant to be sexist out there, fellas. All right, while Jane travels 60 miles, Joe travels 80 miles. And we want to find their speeds. All right, so whenever I teach distance here, I'm going to go ahead and set up a chart. R times T equals D. And who are we comparing in this problem? Well, they always have two comparisons on these type problems. So we'll go ahead and put Joe first, since he comes first in the problem here, and then Jane. Now, what do we know? Do we know how fast they're both going? Well, not really. We know that Joe's going 20 miles an hour faster than Jane. So what we're going to have to do here is use our power of algebra. We're going to have to assign some variables in this problem. So we'll let Jane's rate or speed be x, and then Joe would be what? X plus 20, right. Now, what else do we know in the problem here? It says while Jane travels 60 miles, Joe travels 80. So for distance over here, we'll go ahead and put, all right, Joe's 80 and Jane is 60. And that kind of makes sense out there, doesn't it? Because if Joe is going faster than Jane, well, he ought to be going what? Farther. All right. Now, Young, there seems to be a hole here in my chart. How am I going to find their speeds with this big hole there? And this goes back to formulas, which we're going to talk about later on as well, but we've already discussed them. If we know that R times T equals D, what if I want to solve this equation for T here? I want to get T by itself. I would have to divide both sides by R, wouldn't I? So the time would be distance divided by rate. All right, so since I've got a hole here, they'll usually give you two of the three categories to get the other. So what we're going to do to get the time is we're going to say Joe's time then would be his distance 80 divided by his rate, x plus 20. And we talked about how that's the time the airports estimate the plane's time of arrival. They do the same thing. They take distance divided by rate. Jane's time then would be 60 over x. So it appears we've got our chart filled in, but now how do I get to that equation in disguise that you've always told me word problems are, Young? Well, what we're having to look at here, it says that Jane and Joe really are traveling the same amount of time. All right, so what we're going to do here is we're going to take the times and set them equal here. So let me get a piece of paper here. I'm running out of room. And we're going to take and set 80 over x plus 20 equal to 60 over x. So look familiar here. Yes, we have what? A rational equation. All right. So now we can cross multiply here. 80 times x is 80x. We want to solve for x. Equals 60 times x plus 20. Now, you know what we're going to have to do with the 60 and x plus 20? There's that distributive property, the most important property in algebra, just about. So we'll go ahead and distribute. So we'll end up with 60x plus 60 times 20 is 1200 equals 80x. And to solve for x, we have to get the variables all together. So we'll take the 60x to the left. How? Right, by subtracting. And you can hum yourself a fun tune when you do these. So we end up with 20x equals 1200. And to get x, we're going to divide both sides by the 20. So x is going to come out to equal 2 into 12 goes 6, and you can go ahead and when you divide by 10 and cancel some zeros there, so it's really 2 into 120, and you get 60. Now, did we answer the question here? Let's go back and I'll put that back up here. We found that x was 60, so who's going 60? Jane is. And remember, when you answer word problems, let's put the corresponding units with it. It's 60 miles per hour. So Jane's going 60, Joe's going 80. Joe better watch out or he might find himself in trouble on I-95 there, huh? Yeah. All right, so that's how we do some distance problems. Okay. Let's go ahead and try another one just to make sure we've got that concept down because we don't like to just leave you hanging with one example here on the BCC network. We like to give you lots of examples. All right, the speed of a freight train is 20 miles an hour slower than the speed of a passenger train. The freight train travels 200 miles in the same time that the passenger train travels 300 miles. Find the speed of each train. Ooh, and look at this. Find the distance traveled by each train. So there's all kinds of good stuff we can do here. So I'm going to go ahead and set up my chart here on this page. Let's go ahead and call this rate times time equals, you know what, distance. So whenever you have a problem like that, go ahead and set it up. Now, what two things are we comparing in this problem? Well, we're comparing the freight train to the what? Passenger train. So I'm going to come down here on the side, and I'm going to write freight, and I'm going to write passenger. Okay, now what do we know in this problem? Well, we know the freight train's going 20 miles an hour slower, so this is sort of similar to the last example. We really don't know their speed, so you know which one I'm going to call X in this case. I'm going to call the passenger train X as far as its speed or rate goes. And since the freight train is 20 miles an hour slower, you know what I'm going to call it? X minus 20. Yeah. Now, what else do we know in the problem? Well, we know the freight train travels 200 miles. In the same amount of time, the passenger train travels 300. See, so sometimes students aren't sure where to set numbers up and stuff, but if you think about it, if this one's going slower, it shouldn't be going as far, should it? So that kind of makes sense. Now, gee, there's that hole again for time. What do we do? Yeah, we learned on the last example that the t, if we want to solve in this equation to get it by itself, is going to be the distance divided by the rate. So the freight train's time would be 200 divided by x minus 20, while the passenger train would be 300 divided by x. So we've got our chart all set up. Oh boy, life is good. Now, Young, what do I do with all this again? Now, notice there are some key things in this problem and key wording, and here's one that really stuck out in my mind. In the same time. So when you see this in word problem context, that means, I wonder what I'm going to do with these times here. You know, that translates to these guys are equal, don't you? All right, so let me just sneak up some paper here. So we're going to take the 200 over x minus 20 and set that equal to 300 over x. And we are going to solve and get all of our answers to this problem. All righty, so again, we're going to cross multiply 200 times x is 200x equals 300 times x minus 20 would be written in this manner. And again, similar, we have to distribute. So we're going to get 200x equals 300x minus 6,000. Okay. Now, how did you multiply that so quick, Young? Oh, it's because you're the math teacher. You can do that stuff in your head. Well, it's not really that much rocket science. If you take 300 times 20, 3 times 2 is 6, with how many zeros? Boop, 3. Yeah, so it's not that bad. Now, let's get the x's together. So we'll bring the 300x over, letters left, by subtracting it from both sides. So whenever we're solving for just one variable, letters left, numbers right. So we end up with negative 100x equals negative 6,000. And to solve for x, we can divide both sides by the negative 100. So x will come out to be 60. All right, so that's just another use of rational equations in real life using the distance formula. Now let me look up here and see what the problem asked for. It said, find the speed of each train. So if we found x is 60 here, all right, we can plug in and say, well, the passenger train is going 60, miles per hour, and the freight train going slower would be 40 miles per hour. So we can just plug in for x and get the chart there, right? And sometimes, remember when you do these, like if you come out with an answer that's strange, like 6,000 or 6 million, make sure your answer makes sense in real life. I doubt you're going to find a passenger train that goes 6 million miles an hour, you know, or if you come out with like negative 20 here, you probably didn't plug something into your chart right. So those are always good ways to watch out when you do these. Make sure your answers make common sense. That could be scary anymore, huh? Common sense. Find the distance traveled by each train. Well, gee, we were given that, so we knew the distances here. Now, if we wanted to get the time the trains were going, we could take this 60 and plug it in here, And what would we get? We would get the time is 200 over 60 minus 20 is 40. So it looks like those trains would be going, or 60 here would be going 5 hours because they both traveled the same amount of time. Okay, now let's go back to the graphic here real quick. And let's look at number 3, the work principle. The work principle. Applications involving rational expressions here. And let me talk to the audience here real quick. Now, have you ever worked with somebody that you can do a job in 3 hours and it takes them 6 or 7 hours? I mean, who hasn't? You know, or you might work with somebody and usually that person gets paid more than you too. You know, so that's really bad. But boy, there is a real good use for rational equations, and it's called the work principle. So let me go to that on the examples and we'll show you what it means here. All right, so the work principle says this. Let A equal the time required to do one job, and B equal the time it takes to do the same job. All right? T equals the time it takes both working together to do the one job. So what the work principle says, and there's a couple different ways you can write it, you can write T over A plus T over B equals one job, the time it takes the first plus the time it takes divided by the second to do one job, or you can say 1 over A plus 1 over B equals 1 over T. Now, some of you out there might be going, Young, I'm not quite clear on that. I mean, I don't see where that's working real well. So if you're a boss out there, boy, listen up. This is great for you bosses out there in the audience. All right, here's an example, and I'll show you how it fits. Kelly and Kim want to paint a chair. All right, Kelly can do it in 4 hours, while Kim can do it in 5 hours. How long will it take them working together? All right, so let's go ahead and write down the information here. So Kelly, the word problem says there, can do the job in what, 4 hours? And what, Kim takes a little longer. Now, I don't know if Kelly's a better painter or faster. Maybe Kim does a better job. Who knows? Or maybe they're doing the exact same work here. Now, how long will it take both? That's what the question says. If it takes Kelly 4 by herself, Kim, and you will be amazed at the answers. Like, you might have some construction guys out there. You know that one crew might take 4 hours to do a job and another crew might take 5 hours, and you needed that job done pronto. You have to put both crews on it. How long would it take? All right, so we're going to call both X hours. That's what we're going to call it. Now, we're not really comparing apples with apples here, so we're going to go ahead. Whenever I have problems involving work, I like to get everything in terms of the same thing. So I'm going to say, how about in 1 hour? All right? So if Kelly takes 4 hours by herself to do the whole job, what fractional part of the job could she do in 1 hour? And y'all might say, okay, well, that's 1/4. Kelly could do 1/4 of the job in 1 hour. How about Kim? Well, if Kim takes 5 hours to do the entire job, then the fractional part she could do in one would be 1/5. All right? Now, but we're combining. We're having Kelly and Kim work together. We're combining their efforts. Now, in math, you know what symbol that is? That's a plus symbol. So we're going to combine Kelly and Kim, and we're going to set them equal to the amount of time it takes both. Now remember, this is going to come out a number, so we have to be consistent here. We're going to put 1 over X. So bosses out there, if you know how long it takes certain individuals or crews to do things, now we can say exactly how long it will take them both working together. And this even works if there's more than 2. I mean, there could be 3, 4, 5, and you could keep setting up that same premise. All right, a rational equation in real life? So how do you solve rational equations? What's the common denominator? Now there's more than 2 things here, so we just can't cross multiply. So we're going to go ahead and multiply that equation through by 20x. So I'm going to sneak a 20x in here on both sides. So let me go ahead and get another sheet of paper here, and I will sneak this in here. All right, so we're going to take the 20x over 1 times the 1/4. All right, so we're going to multiply that 20x through here, plus 20x over 1 times 1/5, and we're going to set that equal to the 20x over 1 times the 1 over x. So we know that if we run that 20x through, it'll eliminate all those fractions, and we can figure out how long it takes both to do. And this one's not bad at all, because when we get out the chop, chop, we end up with 4 goes into 4 once, into 20 5 times. 5x times 1, 5x. Plus 5 goes into 20 4 times. 4x times 1 is 4x, equals, over here the x's cancel out, we end up with 20. All right, so collecting like terms, we get 9x is 20. Dividing both sides by 9, we end up with a final answer of x equals 29. So we're dividing bottom into top, 2 and 2/9 hours. So isn't that something? It took Kelly 4 by herself, took Kim 5 by herself, but working together, they can do it in almost half the time of what it takes Kelly, a little over half the time, 2 and 2/9 hours. All right, boy, and you would be amazed, bosses out there, if you know one crew takes 8 hours and one crew takes 10 hours, boy, some of the things that'll come out with this. So these are really good rational equation examples. All right, let's try one last example on the work principle here. All righty. Well, I see a lot of guys out here. We're doing these episodes in the summer, and I just never stop cutting my yard. I wish I had help here, so here we go. Ray can mow a yard in 3 hours on his riding lawnmower. I hate guys like Ray, riding lawnmower. All right, but I'll get over that. Kim requires 9 hours using her push mower. I can relate with her. How long will it take to mow the yard if they work together? All right, so this has a familiar format here. So we're going to come down here and say, all right, Ray riding Ray, we'll call him, can do it in 3 hours, mowing the yard. All right, Kim pushing, poor Kim. That's what I've got there, the old push mower, but that's all right. Takes 9 hours. So we want to see, maybe this is a pretty big lot. It takes her all day. Oh my gosh, that must be some monstrous thing they're mowing there. And then we'll go ahead and put both equals X hours. All right, so again, we're comparing all of these different number of hours together. Let's get it in terms of in 1 hour, and we can compare them better. So how long does it take Ray to do it, and what fractional part of the job could Ray do in 1 hour if it takes him 3 to do the whole job? Right, 1/3. Kim takes her 9 hours. What fractional part could she do in 1 hour? 1/9. And we're going to combine their efforts to get their total time working together. We'll call 1 over x. Now be careful and don't just put x here, because remember, the fractional times you must stay consistent with. All right, common denominator, 3, 9, and x, and the least common denominator would be 9x. So we'll go ahead and multiply the 9x on this one here. So 3 goes into 9x how many times? I'll just kind of run ahead and distribute so I can keep this all on one page here. That'll be 3x. 3x times 1 is 3x. Plus, on the 9x times 1/9, the 9's will chop out, leaving you with plus x equals, and if I multiply both sides, which I must, by 9x, the x's cancel here, leaving me with 9. So again, boy, multiplying through by that common denominator can actually use some of this stuff in real life. What is going on here, young? This is getting incredible, the power I'm feeling in algebra here. So we end up with 4x, collecting like terms, equals 9. Dividing both sides by 4, we get x is 9/4 hours. Now 9/4 hours seems kind of strange, doesn't it? Yeah, so we'll go ahead and divide the bottom into the top, and we'll put 2 1/4 hours. 2 1/4 hours there. All right, so again, boy, they can really do that job quickly there. Ray could have done it pretty fast anyway with that mower, but you would think if he could do it in 3 hours by himself with another person helping him, it will always take less time than the smallest amount. So make sure, again, they make sense when you do them. What do you think? That's good. All right, so let's go back to some graphics now here. And we're going to get back into some formulas involving rational equations. So we've discussed this in previous episodes, but these are going to be a little bit more, have a little bit more bite on them. So to solve a formula for a given variable in review, remember these steps. 1, identify which variable you wish to isolate or solve for. 2, multiply both sides of the equation to clear fractions if necessary. So we're going to have some with fractions in them. 3, get all terms with the variables to be solved for on one side of the equation and all the other terms on the other side. 4, look to multiply or to remove parentheses or factor out a common variable. And 5, as always, solve for the variable in question. All right, so let's look at one of these, and we might pick it up in the next episode and work some more of these out. So we're not just going to leave you with one. Don't worry, follow into that next episode. So here we want to solve this equation for b. 1 over a plus 1 over b equals 1 over t. We have more than 2 fractions, don't we? So what would the common denominator of this be, Young? Well, the most a's, the most b's, the most t's, you would multiply everything through by ABT. Okay, so that would be the common denominator to clear the fraction. So you could even take formulas and adjust them to solve for different variables. And boy, your science instructor will love you if you can do this in science class. This is not just a math concept we're talking about now. This will work outside of math. So if you take the ABT here, we'll set this up, ABT over 1 times 1 over a, so we're going to go ahead and distribute, multiply that through, plus ABT over 1 times 1 over b, we're going to get equal to 1 over t times the ABT, the common denominator, over 1. And you all know what now? We can chop. So I'll take some pretty blues. In these two, we'll chop the a's. In these two fractions, we'll chop the b's. And in these two equal to, we'll chop the t's to get rid of those fractions. So what are we left with? bt times 1 bt plus at, hey, where it's at, we are where it's at here, equals ab. All right, now what are we trying to solve for here? We're trying to solve for b. Now, we have a problem. We've got a b on this side of the equation and a b over here. This is one of the most missed formula problems I see. Doesn't just drive Young crazy, drives the science teachers crazy, drives the students crazy. A lot of students go, okay, divide both sides to get b, Young. We got it from previous lessons. Divide both sides by a, and we will have this thing wrapped up. But you still got a b over here, see? So you don't have b by itself. So what we're going to do is I'm going to take this bt over here and put it with ab to get the b's by itself. And how do I do that? Well, to undo addition, we're going to hit it with, you know what, subtraction. So, hey, where it's at is equal to ab subtract bt. Now, some of you are going, but wait, Young, these aren't like terms. I can't put those together to get b. And you're absolutely right. So what you're going to have to do is use a concept from the past. What comes around goes around. We're getting to that stage. You can factor a b out, leaving you with a minus t. See, so you can isolate the b, and then to get b, you've got b in terms of multiplication. You can divide both sides by the a minus t. Okay, so b, the final answer, will be a times t all over a subtract t. So isn't that neat how it works out here? So always look here, you know, if you can't put two things together, look to factor out that common variable so you can isolate it. See, then we got it in terms of multiplication, then we can divide both sides by that quantity and chop the a minus t's out, leaving us with what we're at. All right, so in closing, remember what it takes to succeed in mathematics. Practice enough to become proficient. Keep all materials organized and don't leave any gaps by missing or skipping lessons because math builds from topics to topic. Be motivated, stay focused, pay attention to detail, and always feel you can succeed. You will be surprised with the results. Take care and we'll see you next time.